Welcome to this session that will present a demonstration of the RFSoC Spectrum Analyzer tool. In this session, the Spectrum Analyzer architecture will be reviewed. Then, there will be 4 demonstrations surrounding the Spectrum Analyzer tool. Demonstration 1 will explore the radio spectrum using the RFSoC 2x2 development board and the Spectrum Analyzer tool. Next, the second-order Nyquist zone will be explored in Demonstration 2 by showing how signals in the Wi-Fi band can be acquired using the Spectrum Analyzer. Then, an experimental frequency planning spectral overlay will be presented in Demonstration 3. As you will learn later, the Frequency Planner is a useful tool to evaluate and understand sources of unwanted frequency spectra. The Frequency Planner has been integrated with the Spectrum Analyzer tool to aid user understanding of signal acquisition using the RFADC. Later, we will explore pink dashboards using the Voila Python library. Voila is an excellent tool that allows users to convert their Jupyter notebooks to lightweight browser applications. Voila is suitable for on-chip application deployment. We will now recap the Spectrum Analyzer architecture described in the previous session. The Spectrum Analyzer uses the Zoom FFT to efficiently inspect and acquire the radio spectrum. RF signals are acquired at the RFADC block and are frequency shifted depending on the requested center frequency of the Spectrum Analyzer. The signal is decimated using the RFADC decimation filters and the flexible decimator in the FPGA logic fabric. Both decimation filters are runtime configurable, meaning the decimation factor can be changed while the system is operational. The system implements a pre-processing window in the FPGA logic fabric. The pre-processing window is essential for suppressing unwanted frequency spurs and spectral leakage. The user can program the window with almost any coefficient to implement time domain windowing. FFT core processing is implemented in the FPGA logic fabric so that it may be hardware accelerated. There are several FFT cores of different lengths in the FFT core processing block. Spectrum post-processing is also implemented in the FPGA logic fabric. In particular, floating point arithmetic is deployed to obtain accurate frequency measurements. Finally, a triple buffer technique is used to write the output frequency domain frames to external memory. The processing system can access external memory and obtain these frames as required. Demonstration 1 on exploring the spectrum will use the Spectrum Analyzer to investigate ambient signals in the surrounding environment. In particular, we will explore the FM radio band, digital audio broadcasting and radio, emergency broadcasts and public radio, television broadcasts, and mobile spectrum access for 4G and 5G communications. The Spectrum Analyzer will be tuned to explore the frequencies in the first Nyquist zone. The corresponding frequency range of the first Nyquist zone is between 0 and 2 GHz. Before starting this demonstration, it is useful to describe the hardware setup of the RFSoC 2x2 and external analog components. The hardware setup for the Exploring the Radio Spectrum demonstration requires a wideband antenna to capture as much spectrum as possible, a low-pass filter to suppress signals in higher-order Nyquist zones, and a variable gain amplifier to adjust the input signal power and improve frequency inspection. The low-pass filter is a DC to 1700 MHz mini-circuits component. The variable gain amplifier is the Nuelec Vega barebones module. And the wideband antenna is a Nuelec Rattlesnake. The diagram on the screen presents the hardware setup for the following demonstration. In this short video, we are going to explore a brand new open source spectrum analyzer tool for Xilinx Ultrascale Plus RFSoC platforms. The spectrum analyzer uses the Zynq software framework for interactive control and dynamic visualization of the radio frequency spectrum. We have a lot of radio spectrum to explore, so let's get started by switching on the spectrum analyzer. Today, we are observing the radio spectrum from Glasgow city centre in Scotland. In the main spectrum analyzer window, we can visualise approximately 1600 MHz of frequency spectra. Several interesting frequency bands can be quickly identified by observing their power in the resulting plot. Starting from the left, the FM radio band can be observed between 87.5 MHz and 108 MHz. The digital audio broadcast band, also known as DAB radio, can be seen around 220 MHz. Emergency radio broadcasts are prominently shown at approximately 390 MHz. TV broadcasts can almost be identified from the nearby Black Hill transmitting station at around 600 MHz to 650 MHz. Finally, several spectrum access bands for 4G and 5G mobile broadcasts can be identified. The first is the downlink spectrum access at around 800 MHz. The second is the public wireless network downlink at around 960 MHz. Capturing such a wide bandwidth using the RFSoC is very exciting to visualize. We can also take a closer look at these signals by applying signal decimation techniques to improve the frequency resolution of the spectrum analyzer window. Let's do that just now and start exploring the FM radio band. The center frequency of the spectrum analyzer can be effectively changed using the widgets currently on the screen. As we can see, we've changed the center frequency to 95 MHz, and we're also changing the decimation factor in a similar way using a drop-down menu. In the spectrum analyzer window, we can clearly see the FM radio band. By decimating further, each of the individual peaks become easier to identify. From the spectrum plot, BBC Radio 2 is shown at 89.5 MHz. BBC Radio 3 can be identified at 92.1 MHz, and BBC Radio 1 is shown at 99.5 MHz. There are various other peaks in the plot, but we won't go through any more of those today. You may not know this, but FM radio stations use 200 kHz of signal bandwidth to transmit audio data. We can decimate further to investigate the bandwidth of the 95 MHz signal on the spectrum analyzer. As shown, the small peak on the screen is approximately 200 kHz wide. Let's now turn our attention to DAB radio at approximately 220 MHz. As shown in the spectrum analyzer, we can identify 5 DAB radio broadcasts. Each band contains several radio stations modulated into a single transmission from a nearby station. Let's continue our exploration of Glasgow's radio spectrum and move to emergency services at around 390 MHz. As shown, there is a cluster of radio transmissions between 391 MHz and 395 MHz. Let's take a closer look by applying further signal decimation. Ofcom is the UK's communications regulator for radio broadcasts and spectrum allocation. They have listed this particular part of the spectrum as business radio and public safety. These broadcasts could very well be used for ambulances, police and fire services in the area. Let's now turn our attention to the digital TV radio broadcasts at approximately 660 MHz. As shown in the spectrum analyzer window, the power of these bands are significantly low. Let's see if we can improve our visualization of these signals using post-processing features of the spectrum analyzer. Let's increase the number of frames that the spectrum analyzer averages across from 6 to 32. This will suppress the noise around the bands of interest. Now, we can manually zoom to improve the range of inspection. From here, each of the bands of interest can be clearly identified. There are several prominent bands, each responsible for broadcasting digital TV around Scotland. From Glasgow city centre, the signal is weak, mainly due to the concrete buildings in the area obfuscating the reception of the signals. We are now approaching the end of our spectrum exploration. Let's have a look at the spectrum access for 4G and 5G mobile devices. Previously, we identified downlink spectrum access at around 800 MHz. According to Ofcom, these bands are owned by Hutchison 3G, EE, Vodafone and Telefonica. They are used to send data from a 4G or 5G radio cell to a user's mobile phone. When data is sent from a mobile phone to the 4G or 5G radio cell, another set of neighbouring frequencies are used instead. We can acquire these signals by inspecting frequencies around 850 MHz. As shown, there isn't very much activity here. There are a few reasons for this. The most obvious reason is that the spectrum analyzer is set to averaging. This means that it will be unable to display signals that are not continuously transmitting. Let's turn averaging off and see if we can identify any bursts of energy. To make finding bursts of energy a little easier, we can use the spectrogram provided with the spectrum analyzer. The spectrogram plots frames of the spectrum analyzer over time. As shown, the spectrogram is able to locate and plot frequencies of high power. These are rolled down the screen. Spectrograms are commonly known as waterfall plots for this reason. There are several settings that affect the display of the spectrogram. We can improve the resolution, or even change the colour map. To improve visualization, a maximum hold can be applied to the spectrum analyzer. This post-processing feature will hold the largest value acquired for each frequency bin of the plot. As you can see, this setup is very useful for inspecting burst transmissions. Let's now finish our spectrum exploration by locating the remaining downlink spectrum access bands that were identified at the beginning of this demonstration. The first is around 945 MHz. Another commonly used band for spectrum access is around 1800 MHz. We have now finished our exploration of the spectrum using a new open source spectrum analyzer tool for Pink and RFSoC. Throughout this demonstration, the frequency spectra in the first Nyquist zone of the spectrum analyzer was explored. Later, we will explore Wi-Fi signals in the second Nyquist zone. Demonstration 2 on the second order Nyquist zone will present how to acquire Wi-Fi signals on the RFSoC 2x2 platform. As shown on the screen, acquiring a signal in the second Nyquist zone is separated into 4 stages. At stage 1, a Wi-Fi signal has been transmitted at 2.4 GHz. The spectrum analyzer is able to receive this signal using the second Nyquist zone. During stage 2, the first Nyquist zone is cleared out so that Wi-Fi signals can alias. An analog bandpass filter is used to achieve this functionality. At stage 3, the signal has been sampled by the RFADC and has folded down into the first Nyquist zone. The signal has folded from 2.4 GHz to 1.6 GHz. The signal frequency band has also flipped and is now in the wrong direction. To correct the direction of the frequency band and demodulate the signal in the negative frequency can be shifted to 0 Hz with a mixer frequency of 1.6 GHz. This correctly demodulates the signal. Before starting this demonstration, it is useful to describe the hardware setup of the RFSoC 2x2 and external analog components. The hardware setup for the second Nyquist zone example requires a Wi-Fi antenna to capture signals in the Wi-Fi frequency band. A bandpass filter is required to clear out the radio spectrum in the first Nyquist zone, and a variable gain amplifier is required to adjust the input signal power and improve frequency inspection. The bandpass filter is a 2.4 GHz to 2.5 GHz mini-circuits component. The variable gain amplifier is the Newelec Vega barebones module. The Wi-Fi antenna is the ANT 2.4 LCW SMA. The diagram on the screen presents the hardware setup for the following demonstration. In this video, we are going to briefly explore the second Nyquist zone of the RFADC samplers. The spectrum analyzer is capable of inspecting 4 GHz of spectrum. Its instantaneous bandwidth is up to 2 GHz. Therefore, we can only calibrate to one Nyquist zone at a time. In this example, we are going to calibrate the RFADCs such that they operate in the second Nyquist zone. This will allow us to inspect Wi-Fi signals at approximately 2.4 GHz. It is important to note that in order for this demonstration to operate correctly, bandpass filters have been applied at the input of the RFADC. Without these filters, it would not be possible to remove unwanted frequency components from Nyquist Zone 1. The unwanted frequency components normally interfere with our signal of interest, which aliases from the second Nyquist zone. As shown, we have switched on the spectrum analyzer. The input of the RFADC is connected to a bandpass filter that passes frequency components between 2340 MHz and 2530 MHz. A wideband amplifier and antenna is also used to improve signal power. Notice that we are currently tuned to Nyquist Zone 1, which ranges between 0 and 2 GHz. The overall power spectrum is clear due to the bandpass filter at the input of our spectrum analyzer. Let's now tune the spectrum analyzer to 2450 MHz. This will allow us to center the frequency plot around the Wi-Fi signals of interest. By decimating, we can improve the spectral resolution of our frequency plot. In order to create Wi-Fi traffic, I have now begun streaming a video over Wi-Fi on my mobile phone. I've placed the mobile phone close to the antenna. Wi-Fi signals are short-term broadcasts transmitted in bursts. By switching the analyzer's post-processing off and turning the spectrogram on, we will be able to visualize the Wi-Fi signals more clearly. You will now be able to see Wi-Fi signals being displayed on the spectrum analyzer and spectrogram. At this point in the demonstration, it is important to explain the underlying operation of the spectrum analyzer and RFADC sampler. Previously, we set the spectrum analyzer's center frequency to 2450 MHz. This widget then sets the mixer frequency of the corresponding RFADC in the low-level hardware. However, the mixer frequency is not the same as the 2450 MHz center frequency previously set. This is because we are attempting to undersample the signal such that it aliases down into the first Nyquist zone. Instead, the mixer frequency is set to 1646 MHz, which is the equivalent frequency used by Nyquist Zone 1. To demonstrate this concept, we will now center the spectrum analyzer around 1646 MHz. If our conceptual understanding of Nyquist zones are correct, then we should see Wi-Fi signals around this center frequency. We will now set the center frequency of the spectrum analyzer to 1646 MHz. As you will now be able to see, the spectrum folded exactly across the Nyquist zone boundary of 2048 MHz. The Wi-Fi signal is now on the right-hand side of the spectrum, as opposed to previously being on the left-hand side. This small experiment shows that our understanding of folding in Nyquist zones is correct. Demonstration 3 is on a frequency planner spectral overlay for the RFSoC spectrum analyzer. As you will learn later, frequency planning is an essential component of RFSoC system design. This example uses the frequency planner spectral overlay to detect the harmonics of a 300 MHz tone. Additionally, the demonstration presents the phase-locked loop mixer spur in the spectrum analyzer window. Before starting this demonstration, it is useful to describe the hardware setup of the RFSoC 2x2. For this example, the RFSoC 2x2 should be set up in loopback mode. This mode requires ADC1 and DAC1, ADC2 and DAC2 to be connected together using an SMA cable. Loopback mode is useful as there is a tone generator in the spectrum analyzer tool. The tone generator will be used to inject the 300 MHz tone into the spectrum analyzer so that several frequency planning features can be used. The diagram on the screen presents the hardware setup for the following demonstration. In this small video, we are going to explore a prototype build of the spectrum analyzer. This particular build also contains a frequency planner control panel, which will allow us to configure a frequency planner overlay alongside the spectrum analyzer plot. Let's begin by switching on the spectrum analyzer. To create stimulus, this example configures the spectrum analyzer design in loopback mode, which allows the designer to inject a tone at their desired frequency and power. By clicking on the Transmitter Control tab, we can now create a tone of 300 MHz at around 0.4 volts. Moving back to the spectrum analyzer window, we should now be able to identify the tone we just created. This look-back configuration is very useful for testing prototype spectrum analyzer features, such as the frequency planner. As you will now see, the frequency planner control panel has just been displayed. There are a number of interesting settings here about the target center frequency and the power of associated spurs in the system. Let's begin by informing the frequency planner that we are interested in acquiring a tone of 300 MHz. We can do this using the center frequency widget at the top of the control panel. Now, let's enable an overlay named RxAlias, which will simply create a new trace in the plot indicating the 300 MHz center frequency. By itself, this part of the frequency planner isn't particularly useful. However, we can enable other features to visualize interesting properties of our spectrum analyzer design. If we enable HD2 and HD3, which are the theoretical harmonics of our center frequency, then we should be able to see the new overlays in the spectrum analyzer plot. The harmonics of our design should be every integer multiple of 300 MHz. Therefore, we would expect to see a harmonic at 600 MHz and 900 MHz. Okay, let's see if we can see these harmonics using the spectrum analyzer by simply configuring the center frequency of the analyzer to 600 MHz and applying appropriate signal decimation techniques to improve spectral resolution. As shown, there is a low power spur at 600 MHz. By all accounts, this is the second harmonic of our 300 MHz tone. However, just to be sure, let's perform a little experiment. Let's change the tone generator to 301 MHz. If our understanding of harmonics are correct, then we should see a new low power spur at 602 MHz. As you can see in the frequency plot, the harmonic has shifted to 602 MHz, which is exactly 2 multiplied by 301 MHz. Notice that the frequency planner overlay did not update. This is because we still need to update it with the new center frequency of 301 MHz. Let's do that now so that the frequency planner overlay displays appropriately. As shown, the frequency planner and the spectrum analyzer are both showing the second order harmonic in our spectrum analyzer loopback design. We should also investigate the third harmonic of our system, which should be located at an integer multiple of 3 around 903 MHz. We can find this harmonic by tuning the spectrum analyzer appropriately. Notice that the frequency planner was also able to calculate the third harmonic. For the purposes of this short demonstration, we are now going to perform one more test using the frequency planner and spectrum analyzer. First, we are going to reset the system and disable the tone generator. From here, we should have a system that does not contain any stimulus. In the RFADC tile, there is a phase-locked loop, also known as a PLL, which is used to generate the clocks for several of the ADC blocks. In the spectrum analyzer design, this particular PLL is driven using a 409.6 MHz clock. By using the frequency planner, we should be able to locate and find the PLL spur. Firstly, let's switch on the PLL image overlay so that we can see its location in the spectrum analyzer plot. The analyzer is reporting that the spur will be at 409.6 MHz. Upon tuning the center frequency appropriately, we can see a low power spur in the spectrum, which is the 409.6 MHz PLL clock spur. In summary, a prototype spectrum analyzer and frequency planner tool has been demonstrated. This tool could be further improved to automatically retrieve information from live spectrum data and conveniently present optimal planning solutions to the user in a dynamic and visual manner. The final demonstration for this session is on Voila and Pink dashboarding for the RFSoC 2x2. Voila is an excellent tool for converting Jupyter notebooks into an interactive dashboard. As shown on the screen, the spectrum analyzer can be provided as both a Jupyter notebook and Voila dashboard application that the user can launch from their web browser. The entire Voila process can be performed on the target device, allowing on-target application development and deployment to be achieved. For this example, there are no hardware setup instructions. Let's now begin the final demonstration. Voila is an excellent tool for rapidly converting Jupyter notebooks into an interactive dashboard. The Pink Spectrum Analyzer comes equipped with a dedicated notebook for launching and creating a dashboard with Voila. As shown, there is a short introduction and setup instructions. In particular, the hardware setup is provided as users will either need to attach an antenna to an RF-ADC or use the simple tone generator to create stimulus. The tone generator is included in the Spectrum Analyzer design and can be used by connecting the RF DACs and RF-ADCs in loopback. In this demonstration, we will use an antenna. There are software instructions for initializing the Spectrum Analyzer dashboard with Voila. The user is simply asked to copy and execute the following code into a terminal. This will launch Voila with a few simple arguments to parse the Spectrum Analyzer notebook correctly. When Voila is launched, it will execute the following 3 code cells and display the outputs for user interaction. Let's now use Voila to convert the Spectrum Analyzer notebook into an interactive dashboard. To begin, copy this command to the clipboard. Now, open a terminal in Jupyter Labs and execute the command. Voila has now been initialized. It is waiting for the user to open a browser window at the local host's IP address, followed by the port number that was set earlier in the command line argument. The Voila server is now in the process of generating the Spectrum Analyzer dashboard. In the background, the Spectrum Analyzer notebook is communicating with a series of handlers that arbitrate commands across the Jupyter Core, MB Format, and MB Convert. The Jupyter client communicates commands between the IPy kernel and the notebook. IPython is then used to communicate with Pink and the underlying overlay. As you will soon see, IPyWidgets is used to provide the user with an interactive interface to control the Spectrum Analyzer design. Finally, the Spectrum Analyzer dashboard has launched and can be switched on using the following button widgets. Similarly, the spectrogram can also be switched on. All of the usual properties of the Spectrum Analyzer can be controlled by the user, such as the decimation factor, which directly affects the spectral resolution. The center frequency can also be adjusted. This now concludes our short demonstration of a Pink dashboard using Voila. In conclusion, this session presented a review of the Spectrum Analyzer architecture. The Spectrum Analyzer was then used for 4 demonstrations. These included exploring the radio spectrum, using the second-order Nyquist zone, working with the frequency planner spectral overlay, and achieving on-target application deployment with Voila and Pink dashboarding.